One, start.
Good morning, everybody. My name is John Williams. I'm a soil scientist with ADAS, and it is a pleasure and a privilege to welcome you to this nutrient management seminar, which is part of the Virtual Grassland show hosted by the Farming Forum. This is the first presentation I've done like this, so we could be in for quite a bumpy ride. Just to say that the presentation is being recorded and will be available for people to listen to later on. Hoping that the presentation will go on for no more than 45 minutes, and there will be opportunity to ask questions during the talk. Just to give you a feel for, if I can get the slides to move, which I'm struggling with at the moment. Just to give you a feel for the content of the presentation. Hang on, sorry, it's not moving on my screen, so we have a bit of an issue here. Here we go. How about that? Look at that. So, the content of the presentation, we will look at the nutrient value of organic materials, the wonderfully valuable sources of crop available nutrients that these materials are. We'll also cover quite a bit on the policies, guidance and regulations that relate to the use of organic materials within agricultural systems, and talk about the management practices that maximise the nutrient value of the materials, but also help compliance with the regulations and policies. A lot of interest in organic matter at the moment and soil organic matter. So we'll talk about how much organic matter is in these materials and what they're like. And at the end, we'll carry out a wee summary and conclusion, and also have the opportunity for questions. And you can write your questions in the question and answer feature in Teams, and my colleague Lizzie Sagoo will be collating the questions during the talk and bring them all together at the end. So I hope that makes sense. So, what is it with these organic materials? Why are they such valuable sources of nutrients? Well, they are, it's fair to say. Typical applications of manures will save significant amounts of money in terms of bag fertilizer inputs. The quantity of nutrients that they supply will vary hugely on the type of material that you've got, but certainly the slurries and the digestates, very good sources of crop available nitrogen. Pig slurry there giving you a typical application of 35 cubic meters per hectare. This pig slurry will supply 63 kilograms per hectare of crop available N if it's supplied in the spring, 72 kilograms per hectare of crop available N from whole digestate. And then we look at the cattle FYM, the solid manures, good sources of phosphate, biosolids. 20 tons per hectare of biosolids will give you a good 220 kilograms per hectare of phosphate. And bearing in mind that a typical wheat crop will take off roughly around about 50, 60, 70 kilograms per hectare of phosphate, then we're looking at enough phosphate for about 3 or 4 crops of wheat from a typical biosolids application. Cattle FYM, so you get amount of potash, and poultry manure, a good balanced fertilizer, 67 kilogram per hectare of crop available N, 136 of phosphate and 168 of potash, only 8 tons per hectare, giving us those sort of applications. And you can see the monetary value associated with those applications in the right hand column of the table. Cattle FYM giving you 40 tons per hectare of cattle FYM has a value of around about 200 pounds per hectare. 35 cubic meters per hectare of cattle slurry, 80 pounds per hectare. So not sort of values that we can ignore when it comes to managing our fertilizer applications. If only it was that straightforward. If all we had to worry about was applying the manures and accounting for the nutrients. Unfortunately, organic manure management isn't straightforward. It's the nitrogen is in two different forms. It's in the organic nitrogen in the solids, and that will tend to mineralize, go into the soil organic matter and mineralize over time. And the amount that mineralizes will depend very much on the weather conditions after applications. If it's warm and wet, then mineralization will occur quite quickly. If it's cold and dry, then mineralization will take a wee while longer. Then the ammonia, which is the immediately available N, is prone to loss by ammonia volatilization. It has nitrifies from ammonium to nitrate, and if we're applying in the autumn time when there's not a lot of crop uptake, then we run the risk of nitrate leaching losses. And then the nitrification process results in nitrous oxide emissions, and as well we have under very wet conditions we could have denitrification occurring, which leads to more nitrous oxide and nitrogen gas losses from the system. So there's a lot of potential losses, and what we've got to do is minimize those losses to maximize the plant's uptake, because if we're able to maximize the amount of nitrogen that's taken up by the plants, then we're minimizing the losses to the environment and we're able to keep everybody happy. So luckily, we've got all these policies, guidance, rules and regulations to keep us on the straight and narrow when it comes to managing the applications of these organic materials. There's the environmental protection regs, there's the code of practices, there's the sludge use in agriculture regs, there's the nitrate vulnerable zone action program, there's the wonderful AHDB nutrient management guide, and also a few new kids on the block, the clean air strategy, which has a code of good agricultural practice to reduce ammonia emissions, which has been recently produced, and we have the farming rules for water, and we have the 25-year environment plan. So there's loads going on and lots of things that we need to think about and comply with. But ultimately, if we're making best use of the manures and we're minimizing the losses, then we're able to comply with most of those rules and regulations. And what I thought I'd do is just quickly go through some of these new kids on the block in terms of understanding what the requirements are likely to be currently and in the future, just to describe some of the practices that we may need to think of when using manures in the future. So the clean air strategy mainly, as far as agriculture is concerned, is dealing with ammonia emissions. It's fair to say that ammonia emissions are a significant pollutant from agriculture and pretty bad news, really. Around about 85% of ammonia emissions come from agriculture, and livestock systems are the main contributor to that, mainly from the handling of manures, the housing, storage and land application of the materials. Anywhere where manure is exposed to the atmosphere, then there is a risk of ammonia emissions occurring. Ammonia is involved in the formation of particulates in air, these PM2.5, PM5 and PM10 particles, which you may have heard of, and they are harmful to human health, particularly respiratory systems, and a lot of concern about that at the moment. Not only that, but 90% of sites of conservation sites and sites of special scientific interest in the UK exceed their critical loads for nitrogen. There's a map on the right hand side there which shows you where the critical loads are being exceeded, and virtually everywhere apart from in the northwest of Scotland, where it's exceeding ammonia nitrogen deposition. Around 65% of that deposition comes from ammonia, and when we have a high, if we have for eutrophication of these special sites of scientific interest and the like, then it takes a long time for them to recover. So it's bad news. So the Clean Air Strategy was published last year, January last year, following consultation in the summer. And in that strategy, it stated that DEFRA will regulate to reduce ammonia emissions and for manure management. That involves covering stores for digestate and slurries by 2027. Those are the high readily available end materials, which have a high proportion of the nitrogen in the ammonium form. Also, rapid soil incorporation for solid manures and solid digestate on tillage land, as long as it's not been direct drilled or not no-till systems, and that will be brought in as soon as possible, and also ban spreading and shallow injection for slurries and digestates by 2025 at the latest. So this is what was published in the Clean Air Strategy last year. And we've got some good evidence base to back up these measures. Certainly, if you can see on the right-hand side there, you've got ammonia emissions from different application techniques for slurry and digestate, where we've got food-based digestate, surface broadcast, trailing shoe, and shallow injected treatments. You can see that where we've used the trailing shoe and shallow injected, we've significantly reduced ammonia emissions compared to surface broadcasting, and it's a similar story for cattle slurry. So, you know, there's excellent evidence there to demonstrate that the techniques are effective at reducing ammonia emissions. The other thing to notice from the graph on the left-hand side is the how rapidly ammonia emissions tend to occur. So, effectively, most of the ammonia emissions happen within 6 to 12 hours of application. So, if we are looking to incorporate materials, then we should incorporate them very soon after application to reduce the potential for ammonia loss. Hang on a minute, my screen seems to have got stuck again, so apologies if this is taking a while to change. There we go. Farming rules for water. Excellent. So we've covered the air, now we're looking at the water. And these were introduced a couple of years ago now, April 2018. There's a couple of paragraphs in those rules which are quite pertinent for the application of organic materials. And that is that the application of organic manures and manufactured fertilizers to cultivated land must be planned in advance to meet soil and crop nutrient needs and not exceed these levels. And planning must take into account where there is a significant risk of pollution, so in terms of how and where we're spreading the materials, application rates, etc., and the results of testing for P, K, Mg, and pH at least every 5 years. And also, you need to determine the soil nitrogen levels by assessing the soil nitrogen supply instead of or testing the soils. So, effectively, you've got to have a nutrient management plan, and you've got to not just look at the fertilizer and manures you're applying, but also the soils. And if the soils are adequately sourced with nutrients, then you have to think very carefully about application rates and whether you should be applying the materials to those soils. So when we're doing a nutrient management plan, what we really need to think about is these 4 relatively simple steps to think about. What does the crop need? Obviously, if we don't know what the crop needs, we don't know how much fertilizer to apply. What's in the soil to start with? Well, you know, if the nutrients are in the soil to start with, then we don't need to worry about applying anymore. If we are applying manures, then it's absolutely crucial to account for manure nutrient supply. And only then do we think about topping up with bagged fertilizer to meet optimum crop demand. So soil analysis, every 3 to 5 years, we have a target pH of 6 for grass, 6.5 for arable. I mean, that's really important because if the pH isn't right, then the nutrient availability is controlled by pH, and it doesn't. If the pH isn't right and we are applying nutrients, it may be that we are using those nutrients very inefficiently if the pH isn't right. We have target nutrient indices of index 2 for P, 2- for K, and index 2 for magnesium. And the graph on the right-hand side kind of sums up the issues really, certainly for phosphate, because the 2 lines with the red and the blue symbols on the left basically show that once you're above index 2, which is 20, well, around about 16 to 25 milligrams per kilogram of Olsen P, then we get very little in the way of yield response. So there's no point having indices higher than index 2 for grass or for arable crops, and index 3 for maize, veg and potatoes, because we're not going to see much in the way of response. And on the right hand side, the lines there show that where they've measured phosphate levels in water from the broad bulk experiment at Rothamsted, when the P status of the soil got above index 4 to 5, then we saw this increase in phosphate leaching losses. Generally, phosphate stays in the soil unless the soil is saturated with P, in which case then there's more phosphate gets into the soil water, which is at risk of leaching. So effectively, what we've got to make sure is we don't get up to these high phosphate indices, index 5 and above, because at those levels, then we're increasing the risk of phosphate loss. So we know what's in the soil. How do we work out how much of the nutrients we're applying from the manures is available to the crop? Well, first of all, you need to know what's in it. Really simple. We need to minimise the nitrogen losses. This is where it starts getting a bit complicated. Bear in mind that diagram that I showed earlier in the talk. We also need to spread the manures accurately and evenly, treat them as fertilizers, and then build them into a nutrient management plan. So we account for the nutrients when we're from the manures when we're working out how much fertilizer to apply. Measuring nutrient content. No one would put a bag of fertilizer in their spreader without knowing what is in the fertilizer, and it's exactly the same for organic materials. We've got some excellent figures in RB209's HDB's Nutrient Management Guide, RB209, Section 2, the organic manures section, which is a really good section to give you good advice and guidance on how to manage manures. There are typical figures there for nitrogen, phosphate, potash, magnesium and sulfur, and also dry matter content. And it's very important that we think about the dry matter content because the nutrient value of the manures varies significantly from farm to farm, partly because of the changes in livestock diet, and also because of differences in the amount of water which is entering slurry systems or digestate systems or whatever. And something which has got 2% dry matter has virtually got 98% water in it, so it's going to be a lot less concentrated than something that's got 6% dry matter and is therefore 94% water. So, you know, it's very important to think about the dry matter content of the materials. Generally on a farm, as long as the feeding regime doesn't change and the livestock type doesn't change, then the amount of nutrients that are in the manures will stay the same. It's just the concentration will vary depending on season. We would have had a lot of very dilute slurries at the back end of last year with all the wet weather that we had in the autumn, but now obviously everything's dried out, so we're looking at a lot firmer stuff to be spreading. As I said, there's variability in nutrient variability caused by a lot of factors, and one of the ways of being able to understand that uncertainty or get better information, more accurate information about the nutrient content of your manures is to get them analysed at a lab, and that again, total N, dry matter, ammonium N, pK, Mg, and sulfur. And if anyone's using poultry manure, it's very important to get uric acid analysed for the poultry manure, because that is a significant part of the readily available nitrogen content of poultry manure. And send them off to a lab for analysis. Costs vary, but probably sort of 50, 60, 80, 100 quid for a sample analysis. And it's very important that the sample that you send to the lab is representative of the material that you're spreading, because if the sample's not very good, then the analysis you get back isn't going to be particularly helpful. And so really importantly, take a representative sample. And again, there's information in section 2 of RB209 to tell you how to take the representative sample. And for those of you who are interested on taking on-farm tests, then we've got these slurry meters, the Quantifix and the Agros meter, which are available in the UK, and they are very good, give very good information on the readily available nitrogen content of slurries and digestates. So they're a very useful tool to use on farm. So spreading, the main things to think about with spreading, obviously, knowing what the application rate is, getting the application timing right, so as we're supplying nutrients at the time that the crops need them, and also being able to spread evenly, which is a significant challenge for a lot of organic materials. So application rates, very important that we match to crop demand. So we must take account of the nutrient content. If we don't know what the nutrient content is and we don't know what the application rate, well, we've no idea how much nutrient we're applying. And so for liquids, for obviously with tankers, then we can know the size of the tanker, but also we need to be able to understand the discharge rate and the forward speed of the tanker to work out the application rate. And clearly we need to understand the area over which the materials have been applied. For solid manures, it's often a question of weighing trailers or loaders empty and full, just to work out exactly how much muck is in the solid manure spreader, because the density of solid manure can vary considerably, which obviously affects the amount of manure that you're getting in a spreader. So stuff that's come out of the house is particularly fluffy, it's got lots of straw in it, will be a lot lighter, will be a lot less dense than material that's been stored for any length of time when it's settled and the straw's broken down, and could be quite heavy. So you could end up with sort of older material, older cattle FYM that's been stored for 6 to 12 months, probably having a bulk density of around about 1, maybe 1.1, whereas something that's come out of the house may well, with lots of straw in it, may be down at about 0.6, 0.7. So even though the spreader's full to the same level, the amount of material that's in the spreader is less. So having kit that has weigh cells on it is very, very useful in terms of being able to quantify how much solid manure you're spreading. Band spreaders, the band spreaders that we use for reducing ammonia emissions are also very, very good at spreading the slurry evenly, slurry and digestate evenly over now known bout widths. And what the benefit of using trailing shoes on grassland and shallow injection on grassland is that we're able to keep the sward clean as well, which means that we can get spread in the spring on growing grass in the spring and not contaminate swards in the same way as if we were to broadcast slurry. You can see from the slide there on the left hand side there's 50 cubic meters per hectare, which is 4,500 gallons an acre, spread with a band spreader. You can just about see a little bit in the wheelings there, and on the right hand side where it's all a bit black and mucky, that's where we've surface broadcast with a typical vacuum tank, and you can see the difference. So not only does it reduce ammonia emissions, spreads it nice and evenly, and it reduces odor loss as well. So using these techniques for slurry is a really good thing to do. So we know what's in it, we know what the application rate is, and we spread it nice and evenly. The next thing to think about is timing. Now these figures here are figures that I'm sure many of you have seen before, but it doesn't harm to make the point again that if we spread high readily available N manures in the autumn, especially on light sandy soils where these data were collected, you can see that in arable situations, and this is on arable land, where we were applying sort of onto stubbles in September and then onto growing crops in October, November, December, January, you can see that the nitrate leaching losses from the September application to these cereal crops was probably equivalent to around about 20% of the total N applied from September applications. And it wasn't until we got to January application timings where the nitrate leaching losses were significantly reduced, and that's purely because on these sandy soil types there's not enough rainfall after application to wash the nitrate beyond 90 centimeters in January, whereas clearly if we're applying in September, you've got all that autumn and winter rainfall which is washing the nitrate below 90 centimeters, and you've got a crop which isn't going to take up much nitrogen between drilling and the end of drainage, well, drilling in October and the end of drainage in March, probably only going to take up 10, 15 kilograms per hectare tops from October drilling. So that means that nitrogen that's in the soil is just going to be at risk of nitrate leaching loss. So autumn application timings are bad news for nitrate leaching losses in arable systems, particularly for slurry and poultry manures. For farmyard manure, for the low readily available end materials like compost, biosolids, farmyard manure, then the risk of nitrate leaching is a heck of a lot lower because obviously they don't have as much readily available N in them, so the nitrate leaching losses are going to be lower because you're applying less in the first place. Now, so effectively on sandy soils, applying in the autumn is bad news because you're going to end up causing nitrate leaching losses. On drained clay soils, though, what we've got to think about there is the fact that water moves very rapidly. When soils are wet, in particular, water moves very rapidly from the surface of the soil through cracks and fissures and into pipe drains, particularly if the systems are mould and we have gravel backfill above the drains. Then there's significant, very quick movement of water from the surface to the drains and into the drains and then into the rivers and all the rest of it. So if we're applying slurries to these drained clay soils, then we have to think very carefully about things like soil moisture deficits, how wet the soil is, how dry the soil is, because obviously if the soil is dry, then the risk of drainfall is significantly reduced. Where if the soils are wet, like they could easily be in the springtime, then you could end up causing significant drainage water pollution with slurry. And this is some work that we did a few years ago now, looking at the impact of different application timings on phosphate, and we also looked at nitrate and ammonium levels in drainage waters. And you can see here from a graph which is looking at total dissolved phosphorus concentrations, that when we applied on the 6th of March, and we had we applied around about 40 cubic meters per hectare of cattle slurry to soil which had a moisture deficit of around about 15 to 20 millimeters, so it was dry enough for us to be able to travel on the surface. We applied the slurry, and then we had about half an inch of rain about a week after the application, and then we had another sort of 3/4 of an inch of rain about 10 days after the application, and we saw a very significant peak in phosphate and also ammonium and in the drainage water after application. So you can see that phosphorus peak there going up to around about 4 milligrams per litre, which is a significant when it comes to phosphorus contamination. We didn't see those levels from autumn application timings because the soils were dry with deficits of around about 100 millimetres. So we would need over 4 inches of rain in order to get the drains to run in the autumn, whereas obviously in the springtime we had a sort of an inch of rain, and within a fortnight of application the drains started to run. And this is what the colour of the water was coming out of the drains. You can see on the left hand side there, that's the treatment pot, and the one on the right hand side is the control where we haven't put any slurry on at all. So you can see the impact of a spring application timing, which was only which was, say, not a mad application rate, 35-40 cubic meters per hectare, and certainly compliant with MVZs in terms of our application timings, but we were causing that level of pollution because the soils were wet. So it's really, really important we think about the soil condition when we're applying to drain clay soils. So that's the nutrients. Brilliant. Now we go on to organic matter. So not only are these wonderful materials sources of valuable sources of nutrients, they're also hugely valuable sources of organic matter. I can't believe you haven't heard how important organic matter is to soils and soil health. A soil is not a soil without organic matter in it. It's just ground up rock, and effectively organic matter controls most of the biological functions in soils, provide a food source for soil biology, which helps with nutrient cycling. The soil biology is brilliant at making aggregates and making the soils nice and stable. The organic matter is brilliant at acting as a sponge and increasing the soil available water capacity of soils, and generally making the soils that much more workable. And for the environmentalists, they also provide a carbon source, so we're potentially able to lock some carbon up into the soil from using these organic materials. So it's great stuff. And you can see here from typical application rates of the manures that we're able to put around about 5.5 tons per hectare of organic matter from a 42 ton per hectare cattle FYM, gives you around about 5.5 tons per hectare of organic matter. Biosolids cakes, similarly good numbers, green compost and green food compost. So there's significant amounts of organic matter that we're able to apply to soils with organic manures. Obviously, the bulky organic materials are going to give us a lot more organic matter than the liquid materials, because of as I said before, 5% dry matter, coal slurry, 95% water. So there's not an awful lot of organic matter in a slurry, whereas a green compost or biosolids cake, which is green food compost, which is 60% dry matter, biosolids cake, which is 25% dry matter, a lot less water in that, and a lot more solid material, organic material, which is from the application. And this is some work that we did a few years ago now, looking at the impact of different application rates, but also different types of organic material on soil organic matter. And you can see where we've applied 50 tons per hectare of organic matter from compost over a 9-year period. Then we've increased the soil organic matter levels by the same amount, where we've applied 90 tons of organic matter from 20 years of FYM applications. So 50 tons of organic matter from compost gives the same increase in organic matter levels as 90 tons of FYM. So suggests that there's something going on there, in that the quality of the organic matter supplied by the FYM is different to that from the compost. And this is backed up by where we looked at the soil, the microbial biomass carbon in the topsoil. We saw that there was a lot more microbial biomass where the FYM had been applied compared to the compost. And we think that's probably because, if you think about the compost, has been through quite a significant processing, where a lot of the available carbon, a lot of the sugars, a lot of the yummy things that the bugs would like to eat have probably gone off in the composting process, and so it's less likely to build up the microbial biomass, whereas the FYM's got lots of lovely sugars and yummy things in, easily degradable organic matter in the FYM, which will build that soil microbial biomass. So not all organic materials are the same in terms of what they bring to soil organic matter. Effectively, if you want to increase organic matter quickly, then potentially using compost would be a good thing. But if you're looking at more nutrients and more increasing the sort of microbial biomass, then using organic livestock manures and FYM in particular would be a good thing to do. So, just to summarise, hopefully I've explained that organic materials are cracking good sources of plant nutrients and organic matter. There are lots of rules and regulations out there, and I know it's quite confusing as to what you've got to do in terms of, or I find it confusing often to understand what I've got to do to comply with these rules and regulations. But effectively, if you manage your nutrients so as you know what the crop requirement is, you know how much is in the soil, you know what the application rate of your manures is, and you know what the application timing is, then you will be able to meet most of the requirements of those rules and regulations. The nutrient management plan is crucial for that. But there's no question that, the way that things are going, that infrastructure investment, particularly in storage and spreading, to reduce ammonia emissions is likely to be needed. And also, manure processing technologies, which I know there are also quite a lot being tested now, and also acidification strategies for reducing ammonia loss. They may well have an important part to play in the management of manures in the future. And yeah, as long as we've got good information, good reliable information, which prove that they work and they're effective, then I think that they show some promise. So thank you very much for your attention. I hope that was of some use and you were able to pick up on it all. I should say that we have applied for fax points for this presentation. So if you'd like to send your postcode and your name, your postcode, and your fax number, either add it to the Q&A session, or you can email it to me on the email there, john.williams@adas.co.uk, and we'll pass those details on basis. And yeah, if you've got any questions now, then I suggest you put them on the system. And thanks very much for listening.
That's great. Thank you, John. We've just got a few questions coming through, and if anyone else has a question, please pop it in the Q&A box. A couple of questions here. So the first one, and this is something that I've heard people discussing and asking about in the past, about composting of farmyard manure in relation to the clean air strategy. Question here, would it be a potential problem in terms of turning farmyard manure and releasing nitrogen in that way rather than it spreading?
Yes, effectively, I think if you're composting anything, as long as it, especially if it's not in a sealed system, but obviously I should point that out at this stage that I'm a soil scientist, not a compost scientist. But the whole point with ammonia, with mitigating ammonia emission, is to reduce the contact time of the ammonia emitting surface with the atmosphere. So if you are if within a muck heap which is obviously heating up and is being turned, then the ammonia emissions that you get from those will be significant. You will increase the risk of ammonia emission. And certainly we did some work quite a few years ago now looking at the ammonia emissions from the storage and land spreading of solid manures, and effectively just leaving the manures open to the atmosphere, just leaving the heat out in the open, ended up there was a crust formed on that, so the ammonia emissions basically went down to virtually nothing after about a month's worth of storage. So extended storage periods for solid manures didn't make a jot of difference to the ammonia loss, but we did see where we turned the manures, we significantly increased the ammonia emission, and that was because you had a heat source there, you were turning it, so you're disrupting the manure and increasing the ammonia emission as a result. So from an ammonia perspective, composting manures, particularly in open windrows, I don't think would be a particularly sensible thing to do. But having said that, solid manures tend to be low readily available end materials, and there's other things you need to think about, like getting a material which is easily spreadable, and composted manure is potentially it's easier to spread and make a better job of evenness of application of a composted product than it is a raw product. So there's a lot to think about here.
Okay, thank you. And another question linked to that in terms of ammonia emissions, and I know you commented about this at the end, is whether adding acid to slurries, acidification of slurries, is something that farmers could practically do to reduce ammonia emissions. Is there anything else you want to comment in terms of that?
We're currently carrying out a DEFRA-funded study in collaboration with Bangor University and Rothamsted, as well as some colleagues over in Denmark, where we're looking at the effectiveness of acidifying slurries and digestate on ammonia loss. And it certainly appears that if you acidify the slurries down to around about 5.5, pH 5.5, then you end up with significant ammonia reduction, sort of 80–90% plus, compared to the unacidified slurries. There are companies which, and obviously the benefit of ammonia of acidification is potentially you could install it in the house, which means that the ammonia emission is abated at the house, and if you keep the pH low, then the ammonia emission is abated at storage and at land spreading. So there's lots of potential positives to it. There are companies out there who are, I understand, installing acidification equipment on farms, and with all these things, there will be some farms where it's relatively easy to install and some farms where it's a bit more difficult. And I think as long as, obviously, you've got to worry about the health and safety implications of it all, and making sure that the slurry doesn't foam, so you're not putting loads of acid in at any one time to the slurry store in particular. We've seen some foaming issues occurring with that. Then it seems to be potentially a very useful technique for reducing ammonia loss. One of the things we are hoping to look at with the study is to see what impact the applications of the acidified materials have on soil quality and greenhouse gas emissions as well. So it's quite a comprehensive project, which we're hoping will give some good information in a year or so's time.
Okay, thanks for that. And another question's just come in linked to that. You've answered the first part of it, but what about costs? Do we know how much these systems cost at all?
I haven't had much conversation. I mean, you'd have to talk to the people who are supplying it to the to the industry. I think JX Agro and Siren are the people that I know of have been involved in producing these bits of equipment. But clearly, there's a cost associated with the acidification, with the acid, and with the equipment that's required to acidify it. But whether and that's one of the things that we really need to think about, and hopefully we'll get some information from the project, is the cost of acidification cheaper than putting up a new slurry store with a lid on it, which we know is very expensive. And obviously, band spreading technologies and all the rest of it, which I think, there's plenty of justification to use band spreading technologies from a nutrient utilization perspective in terms of evenness of application, known bout widths, known application rates and the like. But they're a lot more expensive than normal vacuum tank surface broadcast applications. So that's the thing you've got to think about, is whether the cost of the acidification is a lot cheaper than the cost of the infrastructure that will be required to support the ammonia mitigation strategies. And the other thing I forgot to say is that we're looking to see what the impact of the acidification is on the end use efficiency and sulfur use efficiency of the slurries, and some early information suggests that we're able to pick up the ammonia that we saved in the applications from the acidification. We've been able to pick up that extra nitrogen in terms of yield benefits and quality benefits for wheat. So potentially it's great, but as all of these things, it's the practical application that needs to be sorted out.
Okay, thanks for that. We've had another question in, this one about nitrification inhibitors. So the question is, how do nitrification inhibitors work? I've heard farmers not wanting to use them because they say they destroy the soil bacteria. Should we be encouraging farmers to use them? And are there some genuine concerns that we need to be aware of?
They work by slowing the conversion of ammonium to nitrate, so they impact on the nitrifying bacteria in the soil. They slow down the activity of the nitrifying bacteria. My understanding is that a lot of the work that's been done, that they're used effectively, or have been used very effectively around the world, and the data that I've seen suggests that they're not a risk to soil health at all. Again, it's a question of whether they are, why would you want to use them? There's definite benefits in terms of reducing nitrous oxide emissions, although the effectiveness does vary according to season and soil type in terms of how effective they are at reducing nitrous oxide emissions. But bearing in mind that nitrous oxide emissions are generally less than 1, and in some circumstances around about 0.5% of the total nitrogen applied, from an agronomic perspective, there's not an awful lot of benefit from using them, because the loss pathway that you're impacting on is a very small loss pathway. But environmentally, clearly, that can be quite significant, because nitrous oxide is a pollutant which is 300 times more polluting than carbon dioxide when it comes to greenhouse gas impacts. So it's one of those. I mean, from my perspective, if I was doing it from an agronomic perspective, I wouldn't bother. But if somebody from government told me that I had to do it to reduce greenhouse gas emissions, I'd be quite happy to do it. But obviously, there's a cost associated with that.
Okay, thanks for that. I think that's all the questions that we've had through via the Q&A chat. John has put his email address up there, so I know you'd be happy to take any other questions if anyone wants to email you anything. But just pass back to you, John, in case you had anything else to say before we draw to a close.
No, thanks very much for listening. Hope you found it useful, and yeah, drop us an email if there's anything further you want to catch up on, and don't forget the facts points. Okay. Hope you have a very pleasurable rest of the day.
Thank you.